My name is Tess. I work for Microsoft as a data scientist and software engineer. And I woke up a little bit cold this morning, so I'm going to declare like the first few lines the splash zone, just in case I'm sneezing. No. Anyways, how many of you were here last year when we talked about classical machine learning? Okay, 2. Good. Because I'm going to do a quick recap of classical machine learning before we get into deep learning. Deep learning is what I work with most when I do machine learning, which is pretty much all my day. So, last year I talked about chihuahuas and muffins and doing machine learning to kind of differentiate the two. So, for those of you who are not here, these are 2 pictures. One is of a chihuahua and one is of a muffin. And if you were to distinguish, if you were to use like your domain expertise and figure out what makes one a chihuahua and what makes one a muffin, what would it be? Like random person, what makes you think that this is a chihuahua? You, for example. Yeah, but anything specific, like some features? Yeah, the fur, the eyes, ears, things like that. So around 20 years ago when I went to college and studied AI, this is how we did machine learning, expert systems. And actually, to some extent, that is also how we do machine learning today. A project that I'm working on right now is specifically around expert systems, because expert systems, when you create the rules yourself, has a very nice feature that they're very transparent and they're very interpretable. You know exactly why they choose a specific item. But expert systems and creating all the rules yourself is very human intensive. So they don't really work when you're met with something like this. And you try to, you have to write a lot of rules to distinguish between these chihuahuas and muffins. So then you employ machine learning being that you give a machine a lot of references, like a lot of samples of this is a chihuahua, this is a muffin, and then let the computer come up with the sort of like the details that make a chihuahua and a muffin. So if we go away from expert systems and we look at classical machine learning, last year I also talked about predicting the price of a house, because I had been collecting data for like 10 years to predict the price of a house. I'm very happy to say that 2 weeks ago, we closed on a house, so I no longer have to collect any more data. I did scare the realtor with my Jupyter Python notebooks. She was not as impressed as I thought she would be, but I got it at a good price. However, just to look through what classical machine learning does. So classical machine learning, you have structured data like this, where you're trying to predict something, for example, the price of a house. And you have some input data, like all sorts of information about the house, and what you're trying to come up with is the mapping between the input and the output. So it looks something like this. If you were to use a domain expert, and you would say, okay, so create me a function that sort of maps input to output, and maybe the realtor will come up with some numbers that will work for your specific region or for your specific situation. And life is good until you move to a different location and these numbers don't work anymore. And again, it's very labor intensive. You have to have these realtors, but you could do it. You could create this mapping by computer instead. And the way that would work is something like this. You would take the function, actually if we go back here, you'll see that this is actually a mathematical function. And all machine learning is sort of like mapping data to an equation. So if we just take 2 features, the area in square meters, and try to map it against the price, we'll see it has quite a linear relationship. And what machine learning will do, in this case, using linear regression, is try to figure out how this line fits to the data. So here's a house, 82 square meters for 3.5 million, and so on. Like all these blue dots are instances of houses. To find this line, what it does is it goes like this. It takes a random line, just places some random, we call these weights. But the weights make the line like random. And then we say, how far off are we? How wrong are we in every single instance? Like if we would pick for 82 in this case, we would pick this number instead. How far off are we? So how wrong is this line? And that is what we see here on the right-hand side, and this curve. So we see that we're very, very wrong at this point. And then we try to go down the slope of wrongness until eventually we get to a point where we're as little wrong as we can. Like this is the optimal line, and this is the line that gives us the least errors throughout like the whole data set. This process of finding this optimal solution is called a gradient descent, basically taking us through a gradient down the curve, so to speak. And this orange curve is called a loss function or a cost function. It basically tells us how much the error is, how much does this error cost. And you can see that this is not 0, so we'll never get to a point where we're guessing exactly. Some of the dots will always be a little bit off, but at least we get to the point where we're as little wrong as possible. So this is called linear regression, and the reason I'm bringing this up is because this is sort of how we do classic machine learning. And it's also the basis for deep learning. So now we've guessed the numbers, and we realize that our life is not as linear as we would like it to be. Maybe it's not as easy as mapping something with a solid line. Instead, when you look at house prices, there are other things that sort of interfere. So for example, big houses are really good if they're in school neighborhoods or if they are, family-friendly neighborhoods. But then small houses might be preferable for young adults or places where you're close to bars or something like that. So different types of houses do differently well in different areas. And in order to capture relationships like that, where multiple features combine into getting to the results, you have to create more abstract features like family size and walkability and school quality and things like that. And linear regression doesn't necessarily do that. So instead, what we do is we use something called neural networks. Now we're talking about deep learning. And in neural networks, what happens is we create multiple layers. So in the first layer, we have some really simple features. And the more layers we put, the more abstract features we get. So in here, we learn things like family size. We learn things like walkability and things like that. And it turns out that every one of these small things that we call neurons is actually a linear regression. So every one of these is just the basic classic machine learning, which when you realize that, it's sort of like all fits together, but this way we can learn a nonlinear relationship. And essentially, the deeper we get, the more abstract features we get, but also the more complex our neural network gets and the more it can learn very specific things rather than a more general function that works for, so for example, it would learn very specific things about the houses that it trained on, and maybe not a function that would generalize to new houses. So you have to kind of put a balance in there. So we looked at expert systems. In this case, it's very, very human intensive. Classic machine learning, we can manually create the features, again being quite labor intensive, but then mapping the output through a computer. But with deep learning, we can learn, and the computer can sort of create like this feature extraction for us. So it's quite magical what deep learning can do. On the other end of the spectrum, this is very interpretable. We know exactly how it got to the conclusion. This is very ininterpretable. We don't necessarily know how we got to the conclusion, which causes some problems that I talk about later. But what is so magic about deep learning? So When you look at classic machine learning, you can sort of like only do machine learning on what we call structured data. So data that fits sort of in a spreadsheet, like the house prices, for example. We can do that with deep learning too, but with deep learning, we can also deal with space. So looking at things like images where the position of the pixels is actually important. If we were to do machine learning with classic machine learning on images, we would not see the pixels in a context. Instead, we would see them kind of like as separate entities, which would not necessarily work. And we can also look at things like sequences. So sequences of words, sequences of like temperature that might depend on what the temperature was yesterday or the day before and things like that. We can also do with deep learning. So structure of language, structure of time-based events. And part of the magic of deep learning is that every single one of these hidden layers becomes a representation of the feature input. So we can say if we take an image through a deep learning network or a neural network, in the end we end up with an encoding. And let's say we have like 128 neurons in here, we then end up with 128 number encoding of whatever the image is. This is quite powerful because when you can encode like an image down to 128 numbers, you can suddenly store that in a database, and that becomes like the exact representation of, or not exact, but a very good representation of that image. And another cool thing that we can do is once we get down to the point where we've sort of like encoded it as a number or a string of numbers, we can then reverse the network and do a generator. So in this case, we take in an image of a cat, encode it to its minimal encoding or whatever encoding we want it to be, and then generate another version of that image of a cat that says these specific pixels contain cat, these contain grass and so on, and we can segment out things. So we can sort of like cut out the cat from the image. That is like one thing that we can do with this. We could create something that took a cat and then outputted it as a representation of the same cat, but in the style of Monet, for example. So we can have an encoder and a generator and combine them. So one other way we could use an encoder and a decoder is input an email and generate a response, or input an image and generate a caption. And these sort of work like Lego blocks. Even if this is one of those spatial convolutional neural networks, we can combine that with a generative recurrent neural network. And the magic continues as we continue to combine all these things. So I was talking about encodings before. So this is a way to encode faces. It's called FaceNet from Google. So in here, like all these dots, so these dots are representations of a face of one particular person, in this case, Salma Hayek. In fact, we'll put pictures up here. So I'm the blue dots in here. And we can see, so in this case, we have 128 numbers representing my face, but projected into 2 dimensions. That might sound a little bit like hard to comprehend how you can do that, but if you think of like, if you have a 3D world and you project it into a 2D space, you get a TV screen or a picture of something. If you continue to do that from 128 to 2, you get a representation like this out of 128-bit numbers. But what's cool about this is all my pictures end up in the very same location. So once I have a representation of me that says 128 numbers that I can store in the database, I can then take another picture of me, and it will be similar enough that we can just sort of like do some quick calculations to figure out that, yeah, that's me too. And these encoding models You can either train them yourself, but you could also, like in the case of FaceNet, there are several implementations already that you can use in C# or in Python or things like that to simply encode any old face and compare it to something else. A couple of things that we see here also that you'll see later is that the women tend to end up like closer together because we have similar features, and the men, and here we have some that are a darker shade of pale, end up in like also separated like that. But this here, just remember that, because that's, I'm going to talk about a little bit of a problem with different skin colors and things with things like FaceNet later. And also remember the fact that I happen to end up like in the sort of like midland between male and female, because that's going to become important later too. But having said that, like these representations are pretty cool. Another thing we can do with machine learning or with deep learning is generate from scratch. So in this case, we have NVIDIA. NVIDIA is quite a large player in the deep learning space because they are the only ones who do GPUs that you can do deep learning on at the moment. Like all the common frameworks for deep learning only work on NVIDIA GPUs. So they're the big winners here, but they generate these faces. These faces are not faces of real people. These faces don't exist. They're simply generated from scratch. That is pretty amazing, right? So, now we kind of know a few things that we can do with deep learning. So how does it actually work? If we look at, specifically, we're going to look at how to determine between chihuahuas and muffins. So we're going to use a convolutional neural network because that's for images. And the way it works is like this. We have a lot of input images that we train our model on. And if we let just one image go through the system, like an image of a cat in this case, because I can't draw a chihuahua, in the first layer of a neural network, what it will do is it will find some very simple features. It will find things like lines, colors, things like that. And then as you go further down in the network, or further right, if you will, you end up combining these into more complex or more abstract features. And finally, you end up with something like, if it contains an eye and a nose and an ear, a couple of things like that, it's probably a cat, but it could also, with some kind of percentage, be a muffin. So that is essentially how it works. These layers are built up generally of two things. Convolutions, which are filters, like filters that you normally see and use in, like whenever you do image processing, you might have like a Sobel filter or blur filter or something like that. That's what these convolutions are. And then we have max pooling that compresses the images. So once we've done the encoding, so now we've gotten down to like the 128 numbers for each picture, for example, or more. Then we just tack on a classifier at the end. And this classifier is a regular dense network. It's one of those that you see with all the dots and the neurons. But at this point, we're down to basically a representation with a number. The filters could look something like this. So maybe a filter that finds the left edges or the top edges or something like that. If we were to do feature engineering, we could come up with these filters ourselves. But with deep learning, the cool thing is that the convolutional neural networks actually come up with the filters on their own. So we don't have to worry about what the filters look like. That's what the neural networks come up with. If you look at how this looks in reality, we have something like this. So let's see, if I draw the number 2, in the first step, we're just using some random filters that the machine learning, that the neural network came up with. It then generated these feature maps that's basically with the filters applied. It compressed the images, added some more filters on top of these, compressed them again, and then flattened it out. So at this point, we have the representation. This is like our number of like our array of integers, and then another layer of neurons, and then eventually it comes up with a number 2 from this. So now we sort of know how it works, but in practice, this is what you do. So we want to go ahead and try to determine if an image is a chihuahua or a muffin. The first thing we need to do is find a lot of images that represent chihuahuas and muffins. For this, I'm using 500 images that I've downloaded from Google Search, and I split them up into 3 different categories. I split them up into a training set, which is my majority of my images, maybe 80% or maybe even more. And then I have, so that is what the machine learning model is going to train on. And then I have a validation set, which is what I'm going to sort of figure out if the machine learning is doing the right thing or not. And then finally, when I'm going to iterate through this process a number of times, and finally, when I'm done, I have a small set that I use for testing at the end. So in each time I go through and train my model, the model will pick out batches. So in this case, batches of about 20 images at a time. And it will label some with zeros, so these are all my chihuahuas, and label some with ones. These are all my muffins. So it will randomly pick like 20 images that some are chihuahuas and some are muffins. And then I create my model, and literally this is the code for a convolutional neural network. Like this is how hard it is to write a convolutional neural network. We see convolutions, we say 32 filters, for example, 3 by 3. We then add the max pooling, which is the compression, another convolution, another pooling, flatten it out. At this point, we have our encoding, and then 2 layers, 2 dense layers to do the neural network at the end. And this last part is basically distinguishing between a 0 for chihuahuas and a 1 for muffins. So for very low numbers, it's going to pick 0. For very high numbers, it's going to pick 1, being a muffin. This is how it looks, and this is, I'm just pointing this out because once we're done with this, we now have 42 million variables that the machine learning model will learn. Then we'll go through and compile it, and in the compilation, we then decide what is our loss model going to be, what is our loss function, this orange line, for something where you're going to distinguish between like it's 2 classes, you're always going to use binary cross entropy. And then this part, LR, that's the learning rate. That is basically how fast we're going to descend down this line. And we're going to pick accuracy, accuracy being how many did we get correct out of the bunch. And finally, we just go through and train the model. And we train it using 20 epochs, 1 epoch being 1 pass through the data. And we end up with something like this. And this might be a little bit hard to understand when you first look at it. This will kind of sort of scroll by. But if we look at one of these, the first part here is how long it takes to go through the data. And I wanted to bring this out because a lot of people think it takes a lot of time to do deep learning. And it does if you have a lot of data. But if you only have like 500 images, which honestly is a little bit little for doing deep learning, but we'll see that it actually becomes quite enough. It takes 16 seconds on this machine. Like on just a regular, this is a Surface Book 2. Then we have a couple of interesting numbers. This is the loss and accuracy for the training data and the loss and accuracy for the validation data. So the loss here being, like, what's the difference between 0 and how wrong we are, and the accuracy being how many percent do we get correct? And we want to look for, so what's going to happen is for the training data, we're always going to kind of reach 100% accuracy if we train long enough. But the validation data might not be as good because sometimes, so in this case, we'll reach 91% accuracy. But sometimes, and this happens a lot, we have very high accuracy on the training data, so we have 100%, yet on the validation data, we only have 90%. So we have quite a big difference. And the reason for this is because we're doing something called overfitting. We're learning something very specific about the training material. We're learning maybe that a red pixel in this position means that this is a cat, or this is a dog, or this is a muffin, or something. But that's not sort of generalizable. That doesn't work when we look at the validation data. So we always sort of need to train until we start overfitting and then do something about it. So does anyone have any ideas of what we could do to stop overfitting? Like basically how we can learn more general features from the training data? No. No. So one thing we can do is get more data. That is like the most common way to stop overfitting, because then we're learning like less general, like less specific features about the data. And if we can't get more data just by harvesting more data, a very good way to get more data is by doing something called augmentation. So what we do is like for every single picture here, we modify it a little bit. Like we tilt the image, or we transpose the image so it's like moving up or left or right or something like that. Because then we're not learning this very specific image, but we're learning sort of another version of that image, which on first sight might look like, oh, but we're still learning in the same image, but it turns out very effective because now we can actually understand both dogs looking this way and this way, and it generalizes quite well. The other thing we can do is we can do something called regularization. So what we're doing here is we're saying, forget about a few of the things you learn. Forget about the red pixel. Forget about like the pink bow. Forget about this neuron that picks up, I don't know, noses or whatever. And then for every time we pass through a new batch, we just forget about a random thing to make sure we're not sort of over-focusing on a specific set of information that we find in the training data. So this is called dropout or regularization. And it turns out when we do this, we may not get like to 100% on the training data, but on the other hand, we get quite a lot further on the validation data before we start sort of separating and overfitting. So in this case, we're now up to like 94% with these 500 images and these very simple techniques, and actually a very small neural network. But there is something really magic that we can do at this point. Actually, before we go into that, let's take a look at what accuracy means. So this is something called a confusion matrix, where we say, given 95 muffins or 95 chihuahuas, we got 92 of them labeled as chihuahuas. So we guessed out of the 95 chihuahuas, we guessed that 92 of them were chihuahuas and 3 of them were muffins. Out of the 95 muffins, we guessed that 9 of them were chihuahuas and 86 were muffins. So we were doing a little bit better on the chihuahuas and the muffins, but in general we want sort of this diagonal to be very high, because these are the correct ones, so to speak. We can also look at it like this. These are some of the chihuahuas that we got correct. These are some of the muffins that we got correct. And if we look at the ones that we didn't necessarily get correct, then we can see, okay, so what could we possibly do to get more of these correct? And we'll see things like this picture over here. That doesn't really represent a chihuahua like we would normally, so we ignore the fact that we couldn't find that one correctly. But maybe we should put in more spotted chihuahuas in our data set, or maybe we should kind of ignore the green muffins, I don't know. But in here, by looking at the errors, we can sort of see what we need to focus on a little bit more. But one thing we can do to move from 94% to some really magical numbers is use something called transfer learning. So transfer learning, in transfer learning, we use sort of like what humans use to learn. We use a whole lifetime of learning, and then like in different domains, and then apply it to a new domain. So in this case, what we have is like we have a network that is trained on ImageNet, like a number of million images, where it tries to figure out 1,000 categories, and then we say, just take away the classifier and just give me the encoding of the image, and then I'll tack on my own classifier that will just classify Chihuahua and Muffin, and forget about training on the encoder. We'll just use the encoder as is, but just train the classifier. And when we do this, we get numbers like this with 500 images. So we reached like 100% almost with the classifier. And it turns out that this training just takes like a second or two on the classifier, because it's like the classifier itself is super, super cheap to train. So taking the learnings of the thousands and millions of images and just adding on a classifier on it is very, very effective. In fact, here, where it says 99.47%, that's actually like 100%, only that like there's one image that it sometimes is a little bit unsure of, because I don't have enough test data to, like basically if I have 20 images in my test data, one wrong will make a lot of difference on the percentage. Now, that is like basically how you do deep learning for images. Sometimes, though, you might not actually want to go through and train on your own material or create these models. You could do like the quick prefab and easy way, which is using like computer vision, like cognitive services, just calling an API. But just know that this one is basically like that picture I showed just a moment ago with ImageNet. This is like the one that classifies like 1,000 different categories. And this one, Custom Visions, where you get to train with your own personal data to make a classifier of Chihuahuas and Muffins, for example, this is doing transfer learning. So this is when you take the pre-trained model and then you just add your own classifier at the end. The difference between training on your own and using some of this is that in this case, we've already sort of generated an API for you that you can call from, well, any client you want. Whereas if you create your own model, you would then have to sort of encompass it in an API. Now we have a model. Now the question is, what did we actually learn? Because this turns out to be quite important. It's quite easy to get to the point where you're creating a model, but how do you know that you should actually trust this model at all? Just to give an example, if you have something that's supposed to determine if a credit card transaction is fraud or not, and you have 1 million credit card transactions, out of which 200 are fraud transactions, what would be a good way to get like 99.99% accuracy on something that would determine if a transaction is fraudulent or not? What would you look for? Too late in the day for a question like this. What if I told you there was like a super, super easy and surefire way to get like 99% accuracy on this? What if you select, say, geography? Yeah. Or you could just say all are good. Because if you say that all of them are good, then you would be right 999,800 or 999,800 times out of 1 million, which is 99.98. Does it solve the problem at all? No, not at all. It doesn't tell you anything about what you really want to know, which is which ones are the fraudulent transactions, right? But if you have a really, really imbalanced data set, accuracy is not really your friend. So then you might think, okay, so maybe there is like other ways that we can measure this instead. What if we said we wanted to measure, I wanted to get like 100% accuracy on guessing that the fraudulent transactions are fraudulent. And we can do that too. That is called recall. And we can do that by saying all are fraudulent. And we'll get 100% on the fraudulent transactions, but we'll get like a very poor accuracy instead. So finding the right measurement is quite tricky. In fact, in this case, you would probably want to deal with something like a combination of both precision and accuracy, which is called an F1 score. But just be aware that when someone says accuracy, it doesn't necessarily tell the whole story, especially if you're dealing with unbalanced data sets. The other kind of tricky situation is that you might run into a situation where you didn't necessarily learn exactly what you thought you would learn. So there is correlation and there's causation, and they are not always the same thing. So one example is a model that was created at Microsoft that was supposed to figure out if a heart patient should be an in-hospital patient or an outpatient, so basically treated outside of the hospital. And they were pretty good about the accuracy of the model and everything, but when they looked into what they learned, they found out that everyone who had like asthma was supposed to be treated as an outpatient. Because in the data set, everyone who had asthma had a very high survival rate, which is kind of counterintuitive, but the reason was because they were discovered, their heart problems were discovered a lot earlier because they went into the hospital a lot more often. This is sort of a correlation you don't want, because you don't want to necessarily stop treating people with asthma because the data says that. So let's look at a kind of a concrete example. So this is an example of a model that was supposed to determine if a picture was of a husky, like a greyhound, or of a wolf. This comes from some research called LIME that's used for actually figuring out what a model learns. So if I said that it had like 95 or 98% accuracy, would you trust it? Trick question now that you know that you probably should not trust it. What if I showed you this picture and said that this is what it actually looked at when it determined if it was a husky or a wolf? Then maybe you wouldn't trust it as much, right? So in this case, it turns out that all the picture of wolves had snow in the background, where all the pictures of huskies didn't have snow in the background. So it could quite accurately determine husky or wolf in this data set, but the only thing it really looked at was the background, which was snow. And knowing something like this, so this is a tool called LIME that can tell you on a specific image what exactly made it guess wolf in this case. Something like this is extremely useful and extremely necessary for creating like trustworthy AI, where you know sort of exactly why the system, or at least you have a guess of why the system picked this answer versus the other. It also helps us as software engineers, because if we go through and use this in our testing and find out that this happens to be what it actually learns, then we can go through and remove the background, for example, do another retrain, and make the model learn something a little bit more useful, because now it doesn't have this obvious thing to look at anymore. And then maybe it would learn something like, I don't know, it has bigger teeth or something like that. It would actually make a difference between huskies and wolves. In a similar way, they have an example where they look at a text like this. So this is from something called the 20 news groups dataset. It's a data set that basically has postings in various news groups, and one of the tasks is to figure out which news group did this belong to. So basically classify texts and their categories. And it was supposed to classify the categories of, was this coming to an atheist news group or a Christian news group? And when they trained it, Lime then tells that these are the specific things I look for when I determine that this is an atheist news post. So something that was very important was posting, host, edu, and things like that. And before, if you were told like this is like 99% accuracy, you would probably kind of trust the system. But when you see something like this, you realize that, maybe it's the case that like people in education sort of like have a tendency to post more to atheist news groups. It turned out also that this guy Keith only posted in the Christian news groups. So whenever there was like a post from Keith, it was always a Christian news group. Maybe not as like generic as you would want it to be. But the cool thing about this is that it tells you that while you have good accuracy, it's not a trustworthy model. And it also tells you that we could retrain this by removing the headers and maybe get some better features to look at. The point being that accuracy in itself is not necessarily the clear-cut and trustworthy thing. It's very important that we actually look through and we try to figure out what the model actually learned. Something that you probably also hear, or you probably heard at least at once, is algorithms can't be racist, they can't be biased, they're just math. There's these numbers, so we use machine learning models to kind of get rid of our own biases, our own personal perceptions, and as soon as we create a model, we're sort of creating something neutral that doesn't have feelings and doesn't like something that we can trust a little bit more. And while math itself might not have feelings and might not have any preconceived notions, the problem is that the data we train on most probably does. For example, face recognition. Face recognition is traditionally benchmarked against a data set called label faces in the wild. So this is a data set that I would say like a year and a half ago, like any time you created a face recognition system, you would go to this data set and see how accurate you were against it, because this was sort of like the norm of a representative data set that contained a lot of the variations in the in society. Turns out that this data set that has 1,200 people in it has been gathered from Yahoo News between 2004 and 2008. So on first glance it might be representative, but then you learn that, for example, George W. Bush turns up 500 times in this data set. So 5% of the data set is essentially George W. Bush. Another 5% is Donald Rumsfeld, because they were very much in the news back then. So what we're seeing in training on is a representation of basically how people are represented in the news, which means that this data set is very male, pale, and stale, to be honest. What does that mean then? So one thing it means that if you think about like your own personal surroundings and the people that you know and like the people that you interact with a lot, like for example, I have one Chinese friend. She's a very good friend, but she's basically my only representation of people from China. And if I were to do a lineup of like 10 Chinese people, I would probably not be able to differentiate between them, as well as I could for people with European descent, because we have quite a lot of like in ethnicity bias. I know that people from Europe have different hair colors, they have different eye colors. I know a lot about what differentiates between two people from Europe, but I don't know as much about how to differentiate people from other ethnicities. So same thing when you train a data, like when you train something like face recognition on something where it's only male, very pale people, it doesn't learn necessarily all the nuances of something else. So this is how machine learning thinks of me. It thinks I'm male, which is not maybe a big deal, but it is kind of like, because it doesn't, like, since most of the people in the data set are male, it's always going to favor male. Then it thinks I'm 26, so I can kind of forgive the whole male versus female thing, but yeah. However, when you use a data set like this, like Nikon with their AI for determining if someone blinks, and you suddenly use it in Asia, and everyone blinks because it hasn't been trained on enough Asian people, that generates a problem. Or when you have someone that's darker, that's not even visible to the system, that's a problem. So this is Joy Bulamini. She has to wear a mask whenever she does research with face recognition, because she's just not visible to face recognition. In fact, it turns out that until about a year ago, she was doing a lot of research around this, like representation in data sets. And for white males, like it's almost 100% accuracy in all face recognition systems as far as like what their gender is. But for black females, it's like usually a 37% error. Now, some of the big ones like Microsoft, IBM, a couple of these have retrained their models with more biased data sets to get better, but some are not. And one of the problems when you don't do that is that just like I can't differentiate between some of the ethnicities that I'm not very in tune with, in this case, this was for this summer in the UK, this black guy was sort of picked out of CCTV cameras, and with face recognition, it was determined that he was on the wanted list because face recognition is not very good at determining who is who if you're a little bit darker shade. So these are sort of the problems that we run into because we do things like this. Another typical problem is like this one, where NLP, like natural language processing, is trained on very old sets of text. And the reason why we train on very old sets of text is because we train on things like books that don't have royalties anymore and things like that. So all the free data out there is generally quite old. And we end up with things like this, like, so if you put in, she's a computer programmer and he's a nurse in Google Translate, and translate it to Turkish, which is a gender-neutral language, and then translate it back, you get this. So it automatically sort of switches what is what. This, of course, you can try this out. And the reason I'm not bringing up Bing, because I would if, is Bing actually fixes this by adding a gender non-neutral keyword in here, just to make sure this doesn't happen. But it's a tricky way to, like, it's a tricky and slippery slope to fix these problems. So it's a very political decision of what you do to fix these problems. And that's very tricky. But I think we as engineers sort of have a responsibility to at least raise the questions and make sure the discussion exists. Because things like this end up later on, for example, in Amazon, when they did their, what do you call it? When they took in resumes and figured out which ones they should be giving computer engineering jobs, they totally downplayed anyone who wasn't male. So basically, females never ended up on the top 5 list because of things like this. And they have a very long tail, because you can see this is Google Translate. A lot of things use Google Translate, and then the biases are sort of propagated. So I would say humans have biases, but with AI you can very easily propagate the biases. Now, I don't want to end off on a very somber note, because I feel like the last 20 minutes have been sort of like moving us down like this, but there are very cool things that we can do with machine learning. We can, I'm working on a project where we're trying to figure out if someone has cancer or not in digital biopsy. It's very, very nice. You can find missing people. You can, like, there's all sorts of like nice things you can do. And if you want to do that, like, this is the book to read if you want to get started on real deep learning. Just be a little bit critical when you think about your results. Thank you very much.